this is Nicholas Solomersky from Team 18, and we will be presenting the analysis and redesign of a manual push-reel lawnmower. Our team consists of Peyton, David, Andrew, myself, William, and Claire. The push-reel lawnmower was invented in 1830 by Edward Beard Budding to give a greater cut consistency of grass height on sports fields in the UK. The way it works is as the mower is pushed, motion from the wheels are transferred through a gearbox to spin the blade reel relative to a stationary cutter blade. The height of the grass cut can be adjusted by moving the blade reel and cutter blade relative to the drive wheels. The roller at the rear of the mower provides consistent cutting height as well as visual striping to cut the grass to give it that nice clean look. Our target customers generally are using this for small lawns. Most manual reel mowers have been replaced by powered rotary mowers, which you commonly see in the United States. However, the manual reel lawnmowers are popular in urban areas with small lawns. Push reel mowers are also used professionally to maintain golf course greens and semi-professionally if you have a nice putting green in your backyard. These mowers are chosen for their quietness, precision cut, small size, lack of pollution, and ease of maintenance. Overall, we can conservatively estimate roughly 100,000 units per year sold globally of these type of lawnmowers.
Here's an exploded view of our reel lawnmower. As you can see, we have a variety of parts with multiple different manufacturing processes, from injection molding and die casting all the way to sheet metal bending. The overall complexity and range of parts will give us great opportunity to improve this design for DFA and DfM throughout the project. In regards to assembly, our team has come up with two assembly sequences. First, we have our left hand frame subassembly. Then we will attach the blade reel, then the brush bar, and then attach the right hand frame subassembly, and this will help give the design stability. Then attaching the cutting blade, the roller adjustments, and then turning the assembly to attach the main wheels, and then attach the whole rod subassembly for the final product. In our second assembly sequence, we're going to start with a larger main wheel subassembly, then attach the blade reel, brush bar, cutting blade, and roller all at the same time, then attach a larger right-hand frame subassembly, then attaching the connecting brackets, and then the final rod subassembly for the final part. Based on these two assembly sequences, we have decided that assembly sequence 2 is the superior assembly sequence due to two main reasons: for the ease of testing subassemblies and the assembly structure in parallel. And because of this, we'll be moving forward with assembly sequence 2.
This is our functional analysis for our lawnmower product. The main task function is for it to mow lawns. Breaking it down further, our two primary functions are for the mower to both cut grass and for the user to be able to move the mower across a lawn. Beyond that, all of our other functions fall into one of the four supporting functions discussed in class.
The terminal subfunctions from the FAST diagram and the parts from the fishbone assembly diagram were utilized to create the function component mapping matrix, which illustrates the product functions that are realized by each component. For the push reel lawnmower, there are generally a lot of components that are used to realize each function, with the most components for a single function being 6. There are 6 components to realize 4 of the subfunctions, which are push mower, resist jamming, enable portability, and reduce noise. The redundancies in this matrix show that there are some improvement opportunities via DFA.
This is our bill of materials. We plan to manufacture most parts, except for fasteners and the blade reel, as it is a very complex part. To calculate the material cost of the parts to be machined, we found the necessary volume of the stock material, used density to calculate its weight, and then used the price per weight to get the cost. Similarly, for the plastic parts that will be injection molded, we calculated the volume of the part and used the density and price per weight to get the material cost. For our product, we figured manual assembly made the most sense. To get assembly cost, we multiplied the assembly time by an average wage of $15 per hour. This leads to a total cost of $77.54, a lot of room for optimization.
We classified the parts into the quad chart from their functional importance to their manufacturing and assembly cost. The only parts with high cost are the rod, blade reel, roller, and fasteners. We may need to take a look closer into the rod because of its high cost to its low importance. Based on the FAST diagram, the functions that differ between the customer groups is the cut width. The modules that change are the connection bracket, blade reel, brush bar, roller, and cutter blade. Here are the two variants of the reel mower showing the difference in the width of the blade reel, brush bar, roller, and cutter blade. The assembly sequence can be easily optimized because of the simplistic design of the mower and the minimal variation between the products. 3 sub-assemblies can be made before the differentiation between them. We can take the advantage of this by piecing them together at the end of the assembly.